Hello, everybody, and we are live. John Robson here for the Climate Discussion Nexus, joined by Dr. Javier Vinós, who is author of Solving the Climate Puzzle. And Dr. Vinós, thank you very much for joining us.
Thank you for inviting me, John.
Well, it is a pleasure to have you on the show, and it was a great pleasure to read your book, which I want to start by saying there are two things about the book that really stand out. One of them is you offer this compelling alternative explanation for long-term patterns of heating and cooling of the planet Earth. And the other one is it's an overview that shows how complicated climate is. And I must admit, I'm a little bit nervous that you're going to quiz me on something like the Holton 10 effect and ask me what the difference between that and the Dobson-Brewer effect is, and I may fail. But it is important to realize that when people say the science is simple, they know nothing about it. And I should also probably add your background's actually in molecular biology, neuroscience, and cancer research, but you
Yes.
turned your attention to climate, and you have found that there's something very much wrong with the conventional enhanced CO2 hypothesis.
Yes, that's right. When I got into climate science, I did it just by my own, studying the scientific papers and all the information that I could get about it. And pretty soon I realized that there were a lot of things that didn't match, that the explanation was too simple. Basically, the climate is extremely complicated. It's one of the most complicated things that we can study. It can be compared with studying the human brain, for example. And there's so many parts in that system, and each part is affecting all the others. So the explanation for the enhanced greenhouse effect as the driver of recent climate change has quite a few problems that I go in detail in my book. But basically, there is a problem that it doesn't explain how really the climate has been changing, not recently, but particularly in the past. So, for example, the poles are not showing the right response. Particularly, Antarctica is not warming, and it should, according to the science. And the Arctic, although it is warming, it has been warming basically since 1997, and before that it wasn't warming much. So this doesn't fit that it is an effect from the increase in CO2. And then we have many other problems like this um, 30-year cycle in warming and cooling that it's called the Atlantic multidecadal oscillation, and it happens also in the Pacific. So we have several big systems in the climate system that are not behaving according to what should be expected from them. And we really don't have good explanation for why the climate changes in the way it does. So I think that the problem here is that the answer was decided or established um, too early for our level of knowledge about the climate. And the result of this is that once you think you have the answer, you stop looking for it. So I came from completely outside the climate science. Nobody educated me into the dogma of climate science. So I came looking for answers, and I couldn't find them. All I could find was a lot more questions. And it became very clear to me that such a complexity cannot be answered simply by saying, it's the greenhouse effect, because obviously the greenhouse effect has been in the planet forever. And what we have seen is that the climate in the planet has been changing all the time. So we cannot say that all these changes are due to the change in the greenhouse effect. For example, over the past 10,000 years, the climate has been changing all the time. We had the Holocene climate optimum, and then we have the neoglaciation, and then all along there were a lot of climate events that were very important, and the last one of them was the Little Ice Age, but there have been quite a few of them. I went over this in my first book, and there's over 20 big climate events, and CO2 wasn't there making them, because we know CO2 changed very little for the past 10,000 years. So clearly there are more things, and many of these things are not well known. So saying we already have the answer and we shouldn't discuss this is not the proper way of doing science. And that is why I decided that we needed to investigate more into this and present alternative hypotheses.
Yes, and one of the things that very much struck me about the book, I mean, I was getting into it and trying very hard to get a grip on the dynamics you were talking about with the air and ocean currents. But at the same time, I was noticing, and I was taking obsessive notes on this, the number of ways in which the orthodox theory and the models are unsatisfactory. You've already mentioned there have been a lot of fairly dramatic changes, even within the Holocene, whereas the models say it should only happen in response to changes in CO2, and there hasn't been much of that. We're often told, oh, today's changes are unprecedented, but you point out that they're not. The models can't replicate what's happened in the Arctic or Antarctica. And then you go further into the past and talk about things about the changes in the Oligocene and so on. And then you have this long list of things that the models can't explain, even once we know about them. If I read them all, I'd use up our hour. But it was gradually striking me, and I'm not new to this by any means, that this theory of enhanced CO2 hypothesis driving increases in temperature really fits one slice of the 20th century pretty well, from the mid-1970s on to the end of the century,
That's right.
and almost nothing else. And it's extraordinary how poorly this theory can account for almost any evidence that you care to go and look for, from no matter how far back or indeed how recently, even in the 20th century. This is a theory without evidence. And to some extent, as you said, it's so complicated. On the other hand, we have evidence without a theory. We don't have a comprehensive way of accounting for the other stuff. But this notion that CO2 is the driver just doesn't fit the facts.
That is quite correct. The enhanced CO2 theory of global warming is very unsatisfactory to explain past changes in climate, and even when explaining the cooling between the around 1944 and 1976, it is already failing, and it cannot explain properly the warming that took place in the early 20th century. So why has this theory been so defended and so popular among scientists? Is because scientists need to have a theory. And so far, our level of knowledge is not sufficient to have good competitor for this theory. And therefore, it's like we are stuck with this theory for lack of good alternatives, because our level of knowledge to substitute this hypothesis with others is not very good. So, for example, there are two main things in which the climate system is very unknown. We have very big gaps in our knowledge with respect to two very important things for climate. One is the amount of solar energy that is being reflected by the planet, which this is called the albedo. And the albedo is 29% of the solar energy that reaches the top of the atmosphere is reflected back to space, so it doesn't enter the climate system. And the albedo is one of the most important things in climate, because it regulates the amount of solar energy that enters the system. And this is the main source of energy for the climate, to change the climate. And we really don't know how the albedo changes and how it's regulated, because, for example, both hemispheres have the same albedo. And this is very, very surprising, and scientists cannot explain why, because both hemispheres are extremely different. The southern hemisphere is mainly ocean, which has a lower albedo, and the northern hemisphere is mostly land, which has higher albedo, and a large part of this land is covered during the winter with snow, and snow has a very large albedo. So this difference in the properties of the hemispheres turns out that it's somehow regulated so that both hemispheres have the same albedo, and this is done by clouds. And we don't know why or how this happens, and we cannot even reproduce in models the changes in albedo during the year, because the albedo is not the same all the time. And there are some alternative hypotheses that clouds are regulating the climate. And this obviously, it's perfectly possible. And this has been defended by some scientists, like, for example, John Clauser is a defender of this hypothesis, this cloud hypothesis. And obviously, Spence-Mark proposes that cosmic rays are regulating the amount of clouds on the planet. So the problem is that we cannot answer this question, because our level of knowledge about clouds is just too bad. We don't have good data on clouds in the past, and we don't know very much how they change, because even measuring with satellites, there are so many types of clouds, and they are at different levels in the atmosphere, that we really cannot rule out that this is an explanation for many of these climate changes. And the other part of the climate that we don't understand, that we have a big gap, is the one that I have concentrated the most in my books, because we have better data on it, which is the transport of heat from the equator to the poles. The problem with heat transport is that cannot be measured properly, because we are already discussing how the Atlantic current, the meridional current, is changing, and some scientists are very worried because this could spell drastic cooling for Europe. And other scientists say there's no evidence that this is happening. And the discussion is because we cannot measure the amount of heat that the current is transporting. We can only measure it in certain points. And it's the same with the atmosphere. We cannot measure all the amount of heat that the atmosphere is transporting. So we have a big gap in our knowledge. And I think we could look for alternative explanations to the CO2 theory, precisely where the big gaps in our knowledge are.
And I'm about to get to the key to your the heat transport theory, but I wanted to just mention first, as I was reading the book and noting the kinds of things you were commenting that the models cannot do, they could fit into two categories. They can't really explain the evidence. They can't replicate what's happened in the past. And they also do not properly model these kinds of processes that you're talking about, from clouds to albedo to the way the currents perform. And to segue into the heat transport theory, one of the things you mentioned is that there's this widely accepted, I think it's pronounced Bjerknes, compensation hypothesis, that if heat's been carried one way by the atmospheric currents, it's been carried the other way by the ocean currents. And this way they can more or less disregard heat transport and look at CO2 and total insolation and radiation. But in fact, as you say, empirically, that's just not right. And so am I right to say the core of your theory is that what really drives cooling and warming in the planet is that it warms more than it cools at the equator, and it cools more than it warms at the poles. So it's the amount of heat that gets transported from the equator to the polar regions that then gets radiated back out into space, that looks like the critical mechanism for the Earth's temperature.
Yes, well, that's my hypothesis. And it is based on two things, really. One is that the poles are very, very different. They have very low greenhouse effect. When people talk about greenhouse effect, they think that it is like the same over the entire planet, and it is not. Basically, the greenhouse effect is very strong in the tropics and very weak at the poles during the winter, because as everybody knows, the main factor for the greenhouse effect is water vapor, is not CO2. So water vapor and clouds are about 75% of the greenhouse effect. And in winter, at the poles, there is almost no water vapor, because the atmosphere is so cold that all the water vapor basically condenses out and as snow. And what happens is that this is like having the door of the house opened, because any amount of heat that reaches the poles during the winter, it gets immediately radiated to space and lost by the climate system. So this hypothesis is not really that new. People in the 1960s, 1970s was proposing that changes in heat transport and in oceanic currents transporting heat toward the poles were responsible for glaciations and for ice ages. And this was one of the theories that, for example, the people that defended that plate tectonics was extremely important for climate change, which pretty much has been forgotten nowadays. There's almost nobody defending nowadays that plate tectonics is important for climate change. Well, these people were saying that it was because they alter oceanic currents, and then the humidity from the tropics will be transported to the high latitudes, and this will make the ice expand there. It will precipitate due to the cold weather and low temperatures, and that's the main mechanism by which ice sheets grow and produce ice ages. So it's not really a new theory or anything like that. It's just looking into the data that we now have, which is much better. Since the 1979s, we have satellites and we can measure a lot of things. And the data is quite consistent that there are changes, important changes in the amount of heat that is transported, and that they sort of match quite well some of the changes in climate that we are observing. So when the IPCC talks about climate variability, natural internal variability is called, they are talking essentially about these oceanic oscillations that, like the Atlantic multidecadal oscillation, that affect the temperature of the entire planet. And this is basically whether more heat is being transported towards the poles, or more heat is being retained outside the poles, and therefore we have the oceans warming or cooling depending on where that heat is going. And this is causing that 60-year cycle that is quite well known. So basically, we are talking about heat transport mechanisms. And as I said, the models are not able to answer this question, because the models, and this is important to say it, the models are a product of the human mind. They do not produce scientific evidence. They are basically just human theory in a mathematical form in a computer. So whatever we don't know cannot be in a model. And about the climate, there are a lot of things that we do not know. So therefore, the models are very incomplete. And one of the things is that, as you say, the Bjerne's compensation, that the amount of heat that is transported is thought to be constant. And if this was true, then my hypothesis would be wrong. But we know this is not true because by observing what is happening in the Arctic in the last decades, we can see that a lot more heat is being transported to the Arctic. And that's why it is warming in winter, because we have to think that in winter, the Arctic is in the dark, there's no sun. So the sun is not uh, illuminating, it's not giving energy to the Arctic. So any heat that is in the Arctic in winter has to be transported there. So we have mainly the atmosphere, but also the ocean have been transporting more heat to the Arctic. And if both of them are transporting more heat to the Arctic, then the hypothesis that transport is constant is wrong, and my hypothesis has a better chance of being right.
And also, I mean, there's a paradox here because people who believe in the Orthodox theory will say, oh, look, the Arctic's getting warmer. That proves the planet's heating up. But according to your hypothesis, the presence of more heat in the Arctic actually means the planet is cooling down. And this is why we see more warming in the Arctic, but a great deal less elsewhere, because it's actually being taken to a place from which it's going to radiate out into space.
Yes, that is correct. The thing is that the Arctic doesn't have any capacity to retain heat during the winter. There is a lot of ice, it's covered in ice, so the ice is a great thermal insulator. So the heat has nowhere to go but outside of the planet through infrared radiation. So when there is more heat being transported to the Arctic, what happens is that this heat is escaping the system. So basically, it's like a planet temperature regulation mechanism. And when people are scared about Arctic warming, this actually means the opposite. In fact, one of the problems was for the Orthodox theory was the pause, the hiatus in warming that took place from 1998 to 2014. And the way they erased the pause from the temperature records was by including more Arctic warming into the data sets. So, for example, when changing from HotCrot 3 to version 4, what they did is that to include the Arctic temperatures in places where they are not being recorded because there are no stations, well, they use these algorithms to calculate it. And that way, the Arctic warming was incorporated into the global temperature. And this obviously is just a human decision. But it has a problem because the properties of the Arctic are extremely different. So if we talk about temperature in the Arctic, that means it's very different than talking about temperature changes outside the Arctic. Why? Because the Arctic is very dry during the winter, as I said. And so to change the temperature in the Arctic, you just need to bring a little bit of humidity to it. And what you will see is that temperature can jump about 15 degrees from one day to the next easily, and even more. And this is because the enthalpy, when we're talking about enthalpy instead of temperature, um, very little change in energy in the Arctic produces a big jump in temperature. So in reality, what we have is that temperature records are contaminated by something, temperature in the Arctic mainly, which is the one that it's warming. Um, it's contaminated because we are measuring two different things: temperature changes in places where the humidity is much higher, like the tropics or mid latitudes, and temperature changes in the Arctic, where there is very little humidity, are very different things in terms of energy. So very little energy will change a lot the temperatures in the Arctic. And this energy will leave the planet. So basically, we are looking at this the wrong way. Arctic warming is actually a sign of the planet warming more slowly.
And interestingly, if the planet were essentially a billiard ball, then the heat transport to the poles would be constant through more or less whatever was happening. But it isn't. You've already touched on the important role over time of continental drift and in terms of isolating Antarctica. And in fact, one of the things that's critical right now, Antarctica is very different than the Arctic because Antarctica is so isolated that it's
Yes.
not radiating a lot of heat because not a lot of heat can get in there. And this brings me back to my joking at the beginning about the Holt and Tan effect, because in fact, that's to do with what does or doesn't wall off the Arctic effectively from heat transport. And these are the kind of complexities that have to be taken into account. Whether the polar vortex is essentially putting a wall around the North Pole, or whether and this has to do with this quasi-biennial oscillation. There's so much to remember, but there's this very complicated pattern whereby heat does or doesn't reach the North Pole, and it changes dramatically over time.
Yes, that's correct. The main regulator of the Arctic temperature is the polar vortex. And one of the things that is a problem for the orthodox theory is that Antarctica is not warming, and we have this fantastic correlation between CO2 and temperature during the Pleistocene in the Antarctic cores. And right now, that correlation has been completely destroyed, and nobody's talking about this. But in the only place where we can measure CO2 and temperature for the past 800,000 years, that correlation is completely broken because CO2 has increased a lot and the temperature hasn't changed at all. So this tells us that the temperature does not depend on the CO2 in Antarctica. It depends on the amount of heat that reaches Antarctica from the rest of the planet. And since the polar vortex is very strong in the southern hemisphere, so we have this paradox that is not CO2 but heat transport that regulates temperature there. And if we go to the Arctic, what we see is that the strength of the polar vortex is responding to many factors, and these factors are changing over time. And this is what is responsible for the Arctic warming or cooling in response to changes in the wind speed of the polar vortex. And some of the things that affect the strength of the polar vortex, the northern hemisphere polar vortex, is, for example, solar activity. And this is really something very interesting and very little known, which is that changes in solar activity, which imply a very slight change in the amount of energy that comes from the sun, 0.1% only, are capable of changing the speed of rotation of the Earth. And we don't have an explanation for that. And the only explanation is that changes in solar energy are affecting atmospheric circulation, because the only thing that can change the speed of rotation of the Earth is global changes to atmospheric circulation. And these changes are associated to changes in the polar vortex. So it appears that the whole atmospheric system, it's responding to very slight changes in solar energy. And clearly, this is not because they are responding to the entire spectrum, because that will make the whole thing extremely sensitive to solar changes, which we know it is not. But it is responding basically to the effect on stratospheric circulation that the changes in the UV part of the spectrum during the solar cycle are having. So we have here a mechanism of solar effect on climate that has been studied by very brilliant scientists for many years, that shows a whole cascade of signals that goes from the ozone layer into the strength of the polar vortex. And this part is completely neglected by the IPCC.
Yes. And in fact, I gave the title of your book at the beginning, but I was holding off on the subtitle, but which is The Sun's Surprising Role. And then when I started reading the book and I was trying desperately to get a grip on these various patterns of air circulation and the Dobson-Brewer effect, where warm air rises from the troposphere into the stratosphere in the tropical zone and then gets spread to the poles and so on. And I was kind of wondering when the sun was going to make an appearance, when would dawn come? And I know one of the arguments that people who adhere to the CO2 hypothesis will say, well, total variation in solar activity is not big enough to explain it. Other people, including, of course, Svensmark, have said, no, it's these indirect effects. In his case, the cloud seeding due to its effect on cosmic rays. But then, and speaking of, a theory without evidence and evidence without a theory, I want to quote something from the book where you say the IPCC's sixth assessment report acknowledges that solar activity in the second half of the 20th century was in the top 10% of solar activity observed over the past 9,000 years. This extended period of above average solar activity spanning 7 decades constitutes a grand solar maximum. And then you say, it is absurd to argue that the simultaneous occurrence of the longest period of high solar activity in at least 600 years, along with the period of the most pronounced warming in at least 600 years, is purely coincidental. And so here's the situation where surely the evidence, even if it's hard to see what the mechanism could be, demands that we listen, then the evidence is telling us, look at the sun. And then again, your hypothesis has to do with its effect on ozone and stratospheric air currents, which is it seems like a rather odd and secondary mechanism. And yet, when the correlation is so strong between solar activity and temperature, and you take this back to the Holocene and what happens with the solar minimums, it seems as though something must be linking the sun to temperature.
Yes, the thing with scientists and solar effect on climate is that is very difficult issue because it has been very unsatisfactory for scientists to study solar effects on climate. This goes back 200 years since the first scientists started to look into changes in the sun, trying to correlate it with changes in climate. And after 200 years of failure to really tie solar variations to climate variations, most scientists don't want to continue trying and failing. So they think this issue is sort of toxic for a scientific career, so to speak. And therefore, most scientists have stopped looking into a solar effect on climate. And even in the 1970s, there was a renaissance of this hypothesis, but it was killed when satellites were able to measure the changes in solar activity, and it became clear that the amount of solar energy that changed during a solar cycle was just too small to really affect the climate directly. So the only thing that we have are indirect effects of solar activity. And I came to this question as an outsider, and I said, okay, the sun is clearly a candidate because, as you said, we just had a grand solar maximum. At the same time, we had all this warming, so there's probably some effect here. But when I went, I started on climate, just studying natural climate change, because I thought if we want to know what effect, if any, human actions have on climate, we have first to understand very well natural climate change. And at the beginning, I said, okay, well, there were all these grand solar minima during the Little Ice Age. Well, maybe that was a coincidence. So I started looking for more data through the Holocene, and pretty soon it became very clear that there was a clear association between long periods of very low solar activity and really cold periods during the Holocene. So this looked more and more like a candidate, but I couldn't find, a clear mechanism until I connected all the dots between the importance of heat transport and climate change. And this came through studying certain periods of the distant past when the poles were very, very warm. And this constitutes a riddle because climate scientists cannot understand how the planet at certain times in the past, like in the Cretaceous, or the Eocene, the planet was so warm that there was no permanent ice at the poles, and the average temperature of the Arctic was 14 degrees Celsius for the year. So there were no ice sheets, and sea level was much higher. And they could not understand this because if you think about it, to have such warm poles, you need to transport a huge amount of heat there. But if to transport that heat, you need a big difference in temperature between the tropics and the poles, because the temperature gradient between the tropics and the poles is what really drives heat transport. So they could not solve this riddle. And thinking about it, I came about to the conclusion that like most riddles, the problem is that we were just framing it in a wrong way. And what really was happening was not that during these periods a lot more heat was being transported. Actually, less heat was being transported. But what happened was that heat was not being lost at that time, that was not being lost at the poles during the winter, because the greenhouse effect during those periods at the poles was very strong, not very weak as it is today, because there was no ice and the temperatures were high. So you have humidity in the atmosphere all year round. And probably during the winter, as temperatures decrease, what you would have would be a strong cloud cover and probably fog that will prevent the heat loss at the poles, and that was the reason that the poles were much warmer during these periods. So after thinking about it a lot, I went back to the solar effect, and I said, okay, so maybe solar effect, what is affecting is heat transport to the poles during the winter. And immediately all the pieces started to fall into place, because now we have an explanation for why the sun regulates the strength of the polar vortex, and why the sun affects the speed of rotation of the Earth, because it is all connected into regulating the amount of heat that goes to the poles. I don't know if my hypothesis is correct or not. That will be determined over time, but clearly it could be part of the answer at least. Climate is extremely complicated, and there may be more than one cause that is affecting global warming and climate change during these past decades. But clearly, the sun is being neglected, as many researchers have said, many scientists have said. We are ignoring the sun, and we shouldn't, because there's a lot of paleoclimate evidence that the sun is very important for climate change.
Yes, and part of that, of course, is that if the enhanced CO2 hypothesis essentially enabled people to explain and model all these changes that we think we know about from the past, I mean, not just dealing with centuries or a few thousand years for the Holocene, but going back through the Pleistocene glaciations and back into the Eocene and so on, then it would be fair for them to say, well, there's just not much left for the sun to do, and therefore we are justified in setting up a parameter here that's very low. But the problem is, and again, you documented this in the book in a great deal of detail, that even in the Holocene, where we get rising CO2, but we get this neoglaciation coming out of the Holocene climatic optimum, or you go back and you look at temperature changes for the previous glaciations and interglacials, and CO2 is not triggering the warming, or this problem in the Oligocene where CO2 changes and temperature doesn't. That the big problem is that the one really sort of strong theory that we have doesn't fit the evidence. But then, as you know, with humility, right, it's so complicated. You're not saying you have all the right answers. So we have other hypotheses that are much better compatible with the evidence, but they don't seem rigorous. And there's almost a standoff between this theory without evidence and then all this evidence without a theory. But surely scientists have to say, we follow the evidence in search of a theory rather than the other way around. And I just mentioned in my documentary in 2017, I have a clip from Gavin Schmidt where he's saying how well the models work. And then he shows model projections versus temperature in the 20th century. And there's just no match at all early in the century. And he says, well, that's just noise. Now look how well it comes together at mid-century. And that's because the models were constructed to explain one very small period of time in which CO2 and temperature were rising. And that's what they do. And they do that relentlessly. So when you ask them what's going to happen, they overestimate CO2. When you ask them to explain past periods where they don't correlate, they perform terribly. So that theory really, it seems to me, just doesn't meet the acid test of science. It doesn't fit the facts. And even if we have to retreat to saying, gosh, complex, I mean, you've got problems with the tilting of the Earth that you mentioned, the question of the circulation and the sun's role, continental drift isolating the Arctic and triggering the glaciation there 30 odd million years ago. We may have to admit that the phenomenon is too complex for a grand unified theory, but we can't discard the evidence and because we don't like the fact that we're a bit puzzled by it.
Yes, the evidence I think is there, but the problem with scientists, the scientific research, is that they cannot discard these models unless it is very, very clear that we got it wrong. And we haven't reached that point yet, in which everybody realizes that the models are completely wrong. And therefore, most scientists will stick with what they have rather than throw it away and create a vacuum in which nobody can explain really what is going on, because this is very, very embarrassing for scientists. And there's a lot of careers that depend on it. So there's clearly not a good explanation for many things that happen in climate change, but it is not going to drive a scientific revolution until we have a better hypothesis than the one that it's there. Even the ones that we are proposing, some of us, critics of the Orthodox hypothesis, still need a great deal of evidence before we can challenge completely the Orthodox theory. And part of the problem is the models, because the way the models were built in the 1960s, they are essentially vertical energy transfer models. It's how the energy gets into the system, descends all the way to the surface, and then goes back out. So if you describe the climate in those terms, then you are basically already setting for an answer, which is that any change to the greenhouse effect must be responsible for climate change. But the thing is that these models obviously do not account for the horizontal transfer of energy, which is happening through oceanic currents and through atmospheric uh, movement, atmospheric winds and storms and hurricanes. And all this energy that is moving horizontally is basically discarded as significant just based on assumptions that, for example, that heat that leaves one place in the planet and moves to another one does not change the energy content of the climate system. So therefore, it should not have an effect on climate change, on global climate change. But the thing is that we are forgetting here that the greenhouse effect is extremely uneven in the planet. So every place has a different greenhouse effect, depending on how much humidity the air has, how many clouds are there. So basically, you cannot just average that. And that's pretty much what the orthodox theory does, is to average everything. It averages the energy that comes from the sun, it averages the greenhouse effect, and that leads to confusion and to the wrong answers. So the problem is that these models have become so complicated that they're extremely difficult to change. Basically, one of the problems that scientists have now is that any little change that they made into the models, that they introduce into the models, usually have negative effects on the rest of the model. And this is one of the problems that they're having now with the latest version, the CMIP6, which has a problem because the models run too hot, and this has been recognized in several publications. And what they're doing now is, instead of averaging all the models, they're going to discard that the ones that run hotter to have them perform better. But this is basically analogous to cherry picking the models that give the best answer. But part of this problem is because they have introduced changes that have a cascade effect, because everything in the climate system is interconnected. So one solution could be to try to make completely different models, including certain things like heat transport, and testing for what would be the effects if heat transport is variable and the amount of heat that reaches the poles changes from time to time. But I don't think they're going to try to do that, because they're just too much into the models that they already have. They're very expensive, they require a lot of work, and that's the basis of climate science, because climate science is not an experimental science. I come from an experimental science, from molecular biology, where what every hypothesis that you make has to be confirmed by an experiment. Basically, you design clever experiments that will show you if your hypothesis is wrong. And if the experiment cannot prove that your hypothesis is wrong, doesn't mean that it is right, but at least it gives you a little bit more confidence. And then you go to the next experiment and try to see if it is wrong in another way. And so we were doing all the time experiments, and the main conclusion was it didn't matter how clever we were, most of the hypotheses are wrong, because the amount of hypotheses that a human mind can produce doesn't have any limit, while nature, the universe, has settled for only one. So you're not going to get the right hypothesis, no matter how hard you try. So what you should do is you have to be very humble with about your hypothesis, because nature has a way of showing that most hypotheses are wrong. And if we are now discussing if general relativity is correct or not, because it doesn't explain the speed of rotation of the galaxies, then most probably most of what we think we know about the climate change, it's probably wrong too.
Yes, actually, that was one of the many things I wrote down from the book, is that climatology is not an experimental science, which makes it difficult to test hypotheses. And then the climate models do not reflect reality, so they are not scientific evidence. I think that's such an important point, because at some point, people who are working in the mainstream and are fed up with the fact that the evidence isn't really fitting very well are just retreating into the models. And again, you talk a bit, and people should read the book and about how the models work and how many lines of code they've got, and the ways in which even small changes can throw the whole thing badly out of whack, which is a warning sign that they're not very good models of reality. But one thing that I do want to talk about, we are getting toward the end, but I noticed at a number of points in the book you talk about paradigms, and it just happens because of something else I was doing, that I just gone back and reread Thomas Kuhn's Structure of Scientific Revolutions. And I think clearly part of what's happened here is that a paradigm swept the field in the late 70s and early 80s, that
Yes.
it went almost from being pre-scientific to being, we have a science with a hypothesis. And as you said, one of the difficulties, once you get a paradigm, even one that's not looking all that satisfactory at some point, it's very hard to get rid of it and without having another paradigm, because if you do, otherwise you just sort of go back to pre-science and chaos. And so we
Yes.
have this paradigm that people are wedded to, partly out of career incentives, but partly just because we must make sense of this. And so they're as with the models, where they've gone down this alley where they can't really back out, intellectually too, they can't really back off the CO2 hypothesis, because if they did, they'd say, gosh, situation complex. And it's kind of hard to put that into a PhD thesis.
Yes, that is absolutely correct. This is the way science works, and science. People think that science has been progressing by adding more things, but in reality, what happens is that it runs into the wrong alley quite often, and it takes a scientific revolution to change up the paradigm and get them in the correct direction. So when they talk about this scientific consensus, it doesn't make any sense, because every scientific revolution was made by one scientist demonstrating that all the rest were wrong. You know, if we talk about Copernicus or Galileo, or if we talk about Alfred Wegener or Albert Einstein or Darwin, all of them demonstrated that all the rest of the scientists were wrong. So the scientific consensus has no role in science. And the problem with climate science is that it has gotten into the wrong paradigm, as you say, and it's too reliant on models that clearly are not satisfactory. So it's going to take a lot of time, I think, to change that. But in a way, this has already happened. Alfred Wegener proposed the continental drift theory early in the 20th century, and it took basically half of the century before the science was able to accept it. And when plate tectonics was discovered. So we may be talking about decades, but we should detach what it is, science trying to find its way, which eventually will find it, from policies, and that should not be based on a science that is not solid, clearly. So I don't think scientists should be affecting the way we humans in our societies decide our policies. We have other means to decide policies. Humans have been deciding how to conduct their business and how to do things for thousands of years. without scientists having a final word. So I think we can manage without scientists telling us what we should do, because that's not their job, really.
Yeah, and again, if a politician comes to me and says, "Well, you don't believe that increasing CO2 is going to cause a catastrophic warming, what do you think is going to happen?" And my answer is, I actually don't know what's going to happen. I know that climate is very variable. It's dependent upon a lot of different factors. It's sensitively dependent on initial conditions. I think what you need to do is be resilient. I think you need to try and adopt policies that will make us ready for whatever shows up, because again, and one of the many things that we are told that is untrue is that rapid changes in temperature are unprecedented. And the problem is the proxies wouldn't pick them up going back more than a few tens of thousands of years. But even so, we know with the Younger Dryas, we had very rapid temperature change, not driven by CO2. And the last thing, and I was very struck by this in the book, is that in addition to knowing a huge amount about it, you present it very humbly. And you say there are uncertainties. I don't know I'm right. I wish people would look into this further. And that one of the things that I think has gone rather poisonously wrong, and I suppose it's a weakness among highly intelligent people who found something cool, not a recent one, they're too insistent that they know they're right. And that's why we get lay people saying, "Oh, the science is settled, the science is simple." And again, I was thinking, anybody says that to me, I'm going to send them a copy of your book and say, once you've read this book and could actually answer a quiz on it, come back and tell me it's simple. Because that, again, it's just so mind-bogglingly complicated that I'm going to have to go back and reread it to get all these currents and things so that I can actually talk about them confidently.
Yes, and the climate is a lot more complex that I can grasp. And obviously is reflected in my book. So when they say that this is simple and we have the answer, this is actually a very bad sign, because when we are dealing with very complex things, the most probable thing is that we don't have a good answer to that.
Yeah, and again, I have made this point a number of times that if you take one of these models that supposedly know all and see all, and you feed into it conditions from the 12th or 13th century and ask it to predict the Little Ice Age, they can't do it. The models are actually remarkably feeble, and this is one of the, again, strange phenomena which your book, almost by the way, exposes very dramatically, is the extent to which they have built this tower of certainty upon a foundation of sand. And
Yes.
again, you talk at one point about what the models actually do and the seven variables they all try and take into account, as if seven variables could explain the climate. And then you observe that many of them disagree by as much as 3 degrees about
Mhm.
what the actual current surface temperature is, which is half of the distance between us and the last glaciation. But then they insist, they all say the same thing is going to happen, which sounds to me as though they had the verdict before they held the trial.
Well, by design, the models have been made to be very dependent on changes in greenhouse gases. So what happens is that they cannot explain climate changes of the past when changes in greenhouse gases didn't take place, or took place in the wrong direction. So basically, what we have is a toy computer model which only does one simple answer, which is changes in greenhouse gases. And the thing is that obviously, if they cannot reproduce the climate of the past, and they cannot reproduce many of the things that we observe in the climate, it is clear that they are not going to give us the right answer. But basically, when they say that we should trust the models and all these things, this is all for people consumption, to accept policies that will make them unhappy. So it's clear that models cannot be trusted. That's I think very clear for anybody that studies them a little bit, how they work, and the answers that they give to the climate of the past.
Okay. And we're going to have to leave it there. Our time is up. Again, I want to thank you very much for joining us. And I want to say anybody who wants to get some conception of how the climate works and how complicated it is, you really have to read Solving the Climate Puzzle. It's a marvelous look into it. Again, you're going to be a bit baffled at times. You're going to have to concentrate, but it's well worth the effort. So again, Dr. Vinós, thanks so much for being with us and helping to illuminate this very complicated and important problem. Thank you, everybody, for watching. For the Climate Discussion Nexus, John Robson signing off.
Thank you very much, John.